So class, I'm going to cover section 1.2, which is row reduction and echelon form. And we've talked about this already, a little bit anyways. A rectangular matrix is in what we call echelon form, or you can call it row echelon form, if it has the following three properties. All non-zero rows are above all rows of all zeros. So if you have a row that has all zeros, it needs to be at the bottom. It needs to be below the rows that are not all non-zero. Each leading entry of a row is in a column to the right of the leading entry of the row above it. And we'll talk about what this looks like in a minute. All entries in a column before a leading entry are zeros. Now that would be row echelon form, and you can do, if you get a matrix in row echelon form, you can use what's called back substitution to solve, like we did a minute, in the other previous section. Now if you continue, and excuse me for clearing my throat, but I'm having some congestion here. But if a matrix is in echelon form and it also satisfies these two additional conditions, then it's in what's called reduced echelon form. And then you can actually just read off the solution if there is a solution. So the leading entry in each non-zero row is 1, and each leading 1 is the only non-zero entry in its column. So for example, these matrices are in echelon form. So you notice that if it has a row of zeros, it's at the bottom. And now these values in the boxes could be any non-zero value, and the stars could be any value, including 0. So notice really what we have here is we have our little triangle of zeros right here. So this would be 0, and then everything, that would be what we're going to call the pivot position for column 1. Everything below there is 0. This would be the pivot position for column 2, and everything below that is 0. Now we wouldn't have a pivot position for column 3 and 4 in this case. Here's another example, and so here this row has all zeros. That's okay, but the first non-zero, or a column with a non-zero entry, this is at the top, and below there, that position, which would not be 0, there are all zeros. Now this column actually doesn't have what we call a pivot position, but this one does. So this would be a non-zero number, and everything below it would be 0. This column has what we call a pivot position, and everything below that is a 0. This column has a pivot position, and everything below that on this column is 0. Now we don't have a pivot position here or here. We do have one here. So that would be in echelon form. Now if the two right here are in reduced row echelon form. So if we look at this, we've got the pivot position here and the pivot position here. In addition to there being zeros below the pivot position here, which is 1, there are zeros above that 1. So there are zeros below it and above it. Also, these values, these pivot position values are 1. Okay, here we don't have pivot positions, so it doesn't really matter what these values are. Another example. Okay, so we've got a 1, and we've got a 1 right here, and see, comparing this to this has got to be a 0 to be in reduced echelon form. And then there's the pivot position, so all of the entries above and below that 1 are zeros. This is a pivot position, all the zeros above and below are 0. And then these two columns didn't have pivot positions. This one did. So all the entries above that 1 are zeros. So these are in reduced echelon form, and these are in echelon form. So theorem 1 says the uniqueness of the reduced echelon form. If you get a matrix in reduced echelon form, well, the matrix is equivalent to one and only one reduced echelon form. So it's only one reduced echelon form for each matrix. It wouldn't have another one that's in reduced echelon form. Now, a pivot position in a matrix A is a location in A that corresponds to a leading one in the reduced echelon form of A. A pivot column is a column of A that contains a pivot position. So, for example, this is a pivot position and this is a pivot column. This is a pivot position and this is a pivot column. This is a pivot position and this is a pivot column, and so on and so on. Now, the row reduction algorithm. So this is just an algorithm for what we've already been doing. So the first 4 steps produce a matrix in echelon form, and the 5th step goes a little further and makes it into reduced echelon form. So begin with the leftmost non-zero column. This is a pivot column. The pivot position is at the top. Select a non-zero entry in the pivot column as a pivot. If necessary, interchange rows to move this entry into the pivot position. Use row replacement operations to create zeros in all positions below the pivot. Step 4, ignore the row containing the pivot position and cover all rows, if any, above it. And then you apply steps 1 through 3 to the submatrix that remains. Repeat the process until there are no more non-zero rows to modify. So basically in these steps we're getting the zeros, that little triangle of zeros in the bottom of the matrix. Then step 5 says, beginning with the rightmost pivot and working upward to the left, create zeros above each pivot. If a pivot is not 1, make it a 1 by scaling operations. So in this step, we're getting 1s down the diagonal for the pivots, and we're getting zeros above the diagonal. And then it would be in reduced row echelon form. Okay, here's an example. We want to find the general solution to the system of equations represented by the matrix. Identify the pivot positions in the final matrix and in the general matrix. So I'm going to go over to this page where I worked it out a little bit more. So I look at my matrix. This is a pivot position right here. So what I want to do is I want to get rid of this -1. So I'm just going to add row 1 to row 3. I didn't have to get rid of, if there had been a non-zero entry here, I would have gotten rid of it as well. You could also interchange the rows right here. It doesn't really matter. I'm not sure there would be a reason to do that. But if I just add row 1 to row 3 and make that my new row 3, notice that I get this, and that's going to be my new row 3. And so these are just steps 1, 2, and 3 from the algorithm. Then I look at what I have now. I could have gone ahead and divided this by 4 if I wanted to. But my next pivot position, if I look, because there isn't a pivot position in this column, because that is not going to be a pivot position. A particular row would only have 1 pivot position. So here's the pivot position for row 2, and it's in column 3. And so I want to get rid of this -4 because I'm trying to get, the zeros here. So I multiply row 2 by 4 and add it to row 3. And what I get for then I get zeros here. I get all zeros. So this is what my matrix looks like now. And I've got 2 pivot columns, this one and this one. Now, those are the only pivot columns, columns 1 and 3. Notice row 3 is all zeros. So what that means is, what I've got for my matrix, this stands for x1, x2, x3, x4, the equal sign. And so pivot columns are 1 and 3. The variables corresponding to the pivot columns are called basic variables. So x1 and x3 are basic variables, and x2 and x4 are free variables. So if you wrote out what this matrix represents in terms of equations, it would look like this. You would get these equations, and I could solve this for x1. Now x2 is a free variable. I could solve this equation for x3, and then x4 is a free variable. So that describes the solution of the system. Now, because I have some free variables, and because I had that row of zeros at the bottom, that's another way to think about it. Although I guess it's possible to have a row of zeros and this not be true. But because I have some free variables, the system has infinitely many solutions. So I could let x2 and x4, the free variables, be anything I want. So, for example, if I let x2 be 1 and x4 be 3, the solution would be this ordered quadruple. And this will work in all three equations. So to write it out, you just write out the general solution like this, like we talked about before. Okay, let's go back to our other notes. And they just didn't give a whole lot of description about what they were doing here. But I think we said the same thing. Okay, so Theorem 2 is the existence and uniqueness theorem. A linear system is consistent if and only if the rightmost column of the augmented matrix is not a pivot column. That is, if and only if an echelon form of the augmented matrix has no row of this form. So if you have a row of this form where it's all zeros and then a non-zero number, that means it's inconsistent. If a linear system is consistent, then the solution set contains either a unique solution when there are no free variables, or infinitely many solutions when there are at least one free variable. So you need to remember this. You need to remember how this goes. Then using row reduction, we've really already talked about this. We write the augmented matrix. We use the row reduction algorithm to obtain an equivalent augmented matrix in echelon form. Decide whether the system is consistent. If there is no solution, stop. Otherwise, go to the next step. Continue row reduction to obtain the reduced echelon form. Write the system of equations corresponding to the matrix obtained in step 3. Rewrite each non-zero equation from step 4 so that its one basic variable is expressed in terms of any free variables appearing in the equation. Now here's another example. We want to find h and k, so there's h and k, such that, so there's three different things. One, we want to find it so that there's no solution. One, we want to find it, another, we want to find it where there is a unique solution. And then we want to find h and k where there's infinitely many solutions. So let's look at this example over here where I worked it out. Okay, so first let's do A, where it has no solution. So here are the equations. You can write it as a matrix. And remember, if it has no solution, we have zeros. Well, first let's go ahead and do matrix row operations, because it's not in echelon form yet. So we could multiply row 1 times a -4 and add it to row 2 and replace row 2 with what we get there. And so I get this for row 2. So I'll put that back in here. Now remember, if a system has no solution, then it's going to have a row where you have all zeros here, and this is not 0. So what we want, we've got a 0 here, so we want 8 minus 4h to be 0 and k minus 8 to not be 0. Because that'll give me 0 equals some non-zero number, which can't be true. And it'll be inconsistent. So I want 8 minus 4h to equal 0. If you solve that, you're going to get h equal 2. And you want this not to be 0, so k is not 8. If this is true, h is 2 and k is not 8, the system will be inconsistent because you'll get a 0 here and a non-zero here. Okay, now a unique solution, that means that to have a unique solution, that means that this is not 0. And so we just want 8 minus 4h to not be 0. This could be 0, it doesn't matter, but this is not 0. So this is not 0, so 8 doesn't equal 4h, or h doesn't equal 2. And then for many solutions, we want this position to be 0 and this position to be 0. Because there you get 0 equals 0, which is always true. So I want, for many solutions, both of those positions to be 0. So I get h equals 2 and k equals 8. And that's the answer. And this is just where they did it over here. They didn't really explain it a whole lot, but it's consistent. It has no free variables. Okay, so that's the end of this section. Feel free to ask me if you have any questions. This was 1.2, so hopefully you can do your homework now.